What is up, Precalculus? This is lesson 12.5. We're talking about area under a curve and integration. And the first thing we're going to talk about is just area under a curve. So think about you have a curve, which this is actually one of your first problems here. But if you have some curve and you're trying to find the area between this curve and the x-axis, we have several different ways of maybe estimating that. Okay? And so here's the instructions for this first one. It says, for each problem, approximate the area under the curve. So notice it's approximate. So we're not going to have an exact x here. We're just approximating the area under the curve over the given interval using 4 left endpoints. So we're going to divide our area up into 4 sections, and we're going to use left endpoints. I'll explain that more in just a second. You may use the provided graph to sketch the curve and rectangles. So here is the graph of this. I went ahead and did that before starting recording just to save us a little bit of time because we already know how to graph parabolas. And so we're just going to talk about from -5 all the way up to 3. So we're talking about this area from -5 all the way up to 3, this area right here. So essentially what we're doing is we're wanting to find out what this area is right here. Maybe I can highlight it. All right. What's the area here that I've highlighted in red? Okay, well, there's several different ways you could do that. One way would maybe just be to draw a big rectangle like this, because rectangles are really easy to find the area of. But if you want to be, it would be, I guess, an estimate, but we were going to do more accurate than that. In fact, we're going to use 4 rectangles since they told us specifically 4. And we're going to use left endpoints. We could use right endpoints, but anyways, the idea is we're going to do 4 endpoints. So left endpoints. So notice this whole thing from -5 up to 3 is 8 units long. So it's 8 from here to here. And I could have gotten that from saying 3 minus a -5, which is giving you the 8. And so we're going to take that whole length and divide it by 4, because that's how many sections we have, dividing it by 4. So that gives us 2. So that means each one of our rectangles is going to be 2 wide. So I'm going to start drawing in green here. So one of my rectangles is going to be, that's the first one, next one, next one, next one. That's how wide my rectangles are going to be. Now for the height, I'm going to use the left endpoint they asked me to. So on the left side of this first rectangle, I'm going to go all the way up to the function, and right where it crosses, that's going to be my left endpoint. So I'm going to draw this rectangle. Okay. Now, on the next one here, I'm going to go to my next rectangle. I'm going to use the left side. I'm going to go up here, right here where it crosses. That's where I'm going to draw a cross. For my next one here, I'm going to use this left endpoint. It looks like it crosses right there. So it's going to be this one. And then I'm going to use this last one, left endpoint right here. So notice to estimate the red area, I'm going to use this green area. Now, is that going to be exact? No, but notice I have some extra here and a little under here. A little extra here, a little under here. So it would be a pretty decent estimate to estimate the area under that. So let's go ahead and do that. The area of this first one is going to be, well, I know how wide it is, right? The width is 2. So I just need to multiply it by the height. Well, the height is going to be f of -5. F of -5 is going to give me this height right here at -5. So if -5 times the width, it's going to give me the area of this first one. Then I'm going to add to that the area of the next one. F of -3 times the width, 2. Plus f of -1 times the width, 2. Plus f of 1 times the width, 2. So you can use a calculator if we want. I've plugged it in already. So I'm going to go up on my table to f of negative 5, just to find that. And at negative 5, I get 9.5. So mine's not quite drawn accurately. There we go. So this is going to be 9.5 times 2. F of negative 3 is 3.5 times 2. F of negative 1 is 1.5 times 2. And then f of 1 is 3.5 times 2. So that's going to be 19 plus 7 plus 3 plus 7, so it's going to be 10, 29, 36 units squared. So just to estimate that area is going to be approximately 36 units squared. And I guess maybe you could have just gone through and counted how many boxes we have, but if you counted in there, you'd get something fairly close to 36 units squared. Now, could I get more accurate than that? Well, yes, I could. I could use a trapezoid. There's a trapezoidal rule that uses this endpoint and this endpoint and makes a trapezoid. This one and this one, this one and this one, this one and that one, which would be a lot more accurate if we're just going to use a set number like 4. But this starts getting a lot harder to calculate. Rectangles are really easy, just base times height, or width times height. So if we're going to stick with rectangles, a way to make this more accurate would be to add more rectangles. Instead of having 4, you add 5, or say 6, or maybe even 8, so that way the width is nice and wide. Okay? But the basic idea is that this width that we're talking about here, we're going to divide up into equal pieces, right, where each of these is the same. And that width we're going to call delta x. Just some small width, delta x, some change in x. And I'm going to multiply it by f of x sub I. And x sub I, in this case, is just going to be the left-hand point here. Okay? So if I want this one, it'd just be f of x sub I. And then each of these moves over a delta x. So in my case, my delta x is 2. So notice this is the area of a rectangle of just one rectangle. But then what we're going to do is we're going to sum it up from I equals to 1 up to n. So first option would be if I just used 1, I'd be using one rectangle. N would be how many rectangles I have, right? So we'll just keep going on from there. So you can kind of see if this one was where I started and this is my interval of 2, if I added 2 it'd get me to here. And then if I added 2 of them it'd get me to here. If I had 3 of them it'd get me to here. If I had 4 of them it'd get me to here. So that's my delta x. So we're going to kind of apply this principle, and if we wanted to make this more accurate, what I'm going to do is I'm going to keep adding more and more n's. So what I'm going to have to do is find the limit of this thing as n approaches infinity. So as I get infinitely many n's, then that will actually exactly calculate the area under that curve. So here's another one. Notice we're going to take the limit as n approaches infinity of this summation of this is my function in here. Okay? So we're going to start doing this, and so before we start this, we're going to remember a few of these that we've done before when we're talking about summations. If you have the summation of some constant, n of them, it just comes out to be the constant times n. If you're summing up like some variable I, then it's this. If it's I squared, it's this. I cubed, I to the fourth, I to the fifth. I don't think we're going to get that crazy. We'll probably stick around over here and maybe jump over this way for most of those, but you might want to get these in your notes. So we're going to try to find the sum of this. So what we're going to work with first is just working about the sum of these, and then after we figure this out, then we'll take the limit. So here we go. Let's go ahead and so we're still talking about the limit here as n approaches infinity of this summation. Actually, oh yeah, I can do this. So we're going to do of 3 over n. This is k equals to 1 up to n. And then the same thing, k equals to 1 up to n of 27k squared over n cubed. So notice, if I'm taking the sum of this, I can take the sum of this one and then sum of that one. Technically, I guess I should have parentheses around this thing. Well, notice this piece right here doesn't have any k's in it. That's the k's that I'm plugging in, right? So I can, since it doesn't have any k's in it, I can take it outside of it. So this is still going to be the limit here as n goes to infinity of, open big parentheses, I'm going to have a 3n, and then I'm going to take the sum as k equals to 1 up to n. I'm just going to put a 1 there. Plus, now I'm looking at this one. Notice this is the only part that has a k in it. This part does not. So I'm going to factor this part outside. So this is equal to 27 over n cubed of the summation of k equals to 1 up to n of k squared. Now we can use some of these. I can change this using this one, and I can change this part right here using this one. So we're still taking the limit here as n goes to infinity of 3 over n. And so if it's just a constant, it's going to be c times n. In this case, my c is 1. So it's just going to be times n. So this thing right here is just n plus 27 over n cubed times this, since this is a k squared, is going to be this. N times n plus 1 to n plus 1 all over 6. Okay, let's keep on simplifying down the limit as n goes to infinity. Those n's will reduce, so I just have a 3 here, plus I have an n here that will reduce with that, making it 2. 3 goes into that 2 times, and 3 goes into that 9 times. So I will end up with 9 times n plus 1 times 2n plus 1 all over an n squared. Limit as n goes to infinity of 3 plus, let's see if we can go ahead and expand this out. If you FOIL those, you get this. So I'm going to say 9 over n squared times that thing, 2n squared plus 3n plus 1. Go ahead and distribute this into each of those. Now we're talking the limit as n goes to infinity of 3 plus, that's going to be 18, because the n squared over n squared will reduce, so it's just going to be 2 times 9, 18, plus 3 times 9, which is 27, over n, because one of the n's would reduce, and then plus 9 over n squared. Now, if we're taking the limit of this whole thing, it's the same thing as taking the limit of each of these individually. Now, how does this change as n gets really big? Well, it doesn't change at all. It's just 3. How does 18 change? Well, it doesn't. It's just 18. How does 27 over n? Well, think about some constant number, say 27, I divide it amongst 5 people. Everyone gets more than 5. If I divide amongst 10, now you're getting 250. If I divide amongst 100, now you're getting 25 cents, right? 27 cents. So the bigger that this gets, the closer this thing goes to 0. So as n approaches infinity, this term approaches 0. Same thing with this. In fact, this one even approaches 0 faster. So this would be plus 0 plus 0. So this would be 21. So the area under this curve would be 21. Alright, so this is a new symbol. This is called the integral symbol. And really what this means is just the limit as n approaches infinity of the summation of I equals to 1 up to n of the function evaluated at x sub I times delta x. Delta x is equal to b minus a over n, where this is b and this is a. So that's going to be 3 minus 0 over n, which is just 3 over n. And then x sub I is equal to a plus I delta x. So your starting point plus I, which term you're talking about, times that width. So that width is this. So this is going to equal to, again, the a is 0 plus I times 3 over n. So that's 3i over n. So now let's use this x sub I and this delta x in here to evaluate. So this whole thing is equal to the limit as n goes to infinity of the summation of I equals to 1 up to n of 2 times 3i over n minus 1 times 3 over n. So as this is multiplying by the summation, so I'm going to write it in front instead of after it so I don't get it confused. So this is going to be the limit as n goes to infinity of 3 over n. And then I'm going to find the parts of this that does not have an I in it and put it out in front. So I'm going to write a big, so this is going to be 6 over n times the summation of I, and then minus 1 times the summation of 1. Well, if I keep my finger there on page 777, it's going to be the same thing as the limit as n goes to infinity, 3 over n times 6 over n times n plus 1 over 2. Again, this thing right here is the same thing as this, minus 1 times, this thing just becomes n, so thing becomes n times 1, so n times 1. Let's clean this up a little bit here, n and n reduce. 2 goes into 2 1 times, into that 3 times. So I'm going to have the limit as n goes to infinity, 3 over n times 3n plus 1 over 1 minus an n, which would be the limit as n goes to infinity, 3 over n times 2n plus 1 up here, the limit as n goes to infinity. I'm going to distribute that in. That's going to be this times this. The n's would reduce and just give me 6 plus 3 over n. Now, as n changes, 6 does not change. So this part right here, I guess, would just go to 6. It just stays the same. But 3 divided by a number that keeps getting bigger and bigger and bigger is going to approach 0. So this whole thing is going to equal to 6 plus 0, or 6. So the area under the curve of this from 0 up to 3 is going to be 6. This is one of your homeworks. So are the 2 on the previous pages, so make sure you copy these answers onto there. And good luck. Let me know if it can help you more.